Now let's talk about resistance and resistivity. Electrons in a conducting material are accelerated in between collisions with lattice ions in the presence of E field. So this means velocity, the drift velocity, is proportional to the E field. We know from the last movie, current density is proportional to Vd, right? So this implies J, or current density, is also proportional to electric field. If you replace the proportionality constant, we get J equals sigma E, where sigma is now going to be called electrical conductivity. So electrical conductivity is by definition sigma E, where sigma is the electrical conductivity of the material. If the sigma is large, then the material is a good conductor. It is an intrinsic property of the material, and it is not a property of any shape, size, or sample of the material. The unit for conductivity is Siemens per meters. More commonly used term used to characterize a material is ρ, where ρ is the resistivity. And resistivity is given by definition equals to 1 over sigma. If J is sigma E, then current density is equals to 1 over resistivity E, or E equals ρj. The unit for resistivity, or SI unit for resistivity, is ohm meter. For a perfect insulator, resistivity will be infinity and sigma will be 0. There are a couple of things that we need to talk about when we talk about resistivity. So we know E equals ρj, where E is electric field and J is the current density. For some material, resistivity is not constant, but it depends on the strength of the applied field. For others, the resistivity is completely independent of the strength of the applied field. So those materials where the resistivity is not constant are called non-ohmic materials. The materials where the resistivity is independent of the strength of the applied field are called ohmic materials. However, we have to keep in mind that when external electric field becomes sufficiently high, nearly all materials will behave like non-ohmic materials. What is Ohm's law? So Ohm's law states E equals ρj. The resistivity or conductivity of a material is independent of the magnitude and direction of the applied field. Or equivalently, it states the resistance of an object is independent of the magnitude or the sign of the applied potential difference, where R is going to be given by rho L over A, where L is the length of the conductor and A is the cross-sectional area. More commonly recognized form of the Ohm's law is delta V equals IR. For ohmic devices, we get the value of R for any of the applied potential. For non-ohmic devices, we get the value R depending on the value of the applied potential. So this plot on the left shows you IV plot for material that obey Ohm's law. And this one here shows you the plot for materials that do not obey Ohm's law. For example, a PN junction diode does not obey Ohm's law. A microscopic view of Ohm's law says if you want to make sure that the direction of applied field is in this way, the solid line will be electron moving from point X to point Y. So it will go basically from here to 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 here. So the dashed line represents the path might have been in the presence of the applied field. However, in both cases you will note that there is a gradual but steady drift in the direction of the E field. The resistivity of material varies by an enormous amount. Metals have large number of delocalized or free electrons that are not stuck in one place, but free to move about over large distances. Hence, they have very little resistivity. An insulator, each electron is tightly bound to a single electron, and a large force is required to pull it away. Hence, insulators have very large resistances. Semiconductors lie between the two extremes. They will have some free electrons and most bound electrons. So electrical resistance can also be defined in terms of Ohm's law as the ratio of the potential difference or voltage delta V across a conductor to the current through the material. R equals delta V over I. The SI units of resistance are called ohms. So how do we measure resistance? The resistance of any material with a uniform cross-sectional area is determined by following factors: the material itself, the length of the material, the cross-sectional area, and the temperature. This is very important. Higher the resistivity of a conductor, the higher the resistance. The longer the length of the conductor, the higher the resistance. The lower the cross-sectional area of the conductor, the higher its resistance. And the higher the temperature of the conductor, higher its resistance. So copper is the most widely used material because it is quite malleable, ductile, and available. Aluminium was tried for general wiring, which created difficulties due to its thermal characteristics. Silver and gold are used, but because of their cost, they have been limited to places that justify the cost. Tungsten has a resistivity 3 times that of copper, but there are occasions when its physical characteristics, durability, and hardness are the overriding consideration. So as we just talked about, resistivity depends on temperature. As the temperature of most conductor increases, the increased motion of particles within the molecular structure make it increasingly difficult for the free electrons to pass through, and the resistance level increases. For most materials, the relation between the resistivity and temperature is linear over a large range of temperatures that we deal with every day. So the formula that to use for resistivity and temperature dependence is rho equals rho naught 1 plus alpha delta T, where rho is the resistivity at the temperature you are looking at, rho naught is the resistivity of the temperature T0, alpha is the temperature coefficient of resistivity. So good conductors, an increase in temperature will result in the increase in the resistance level. Consequently, conductors will have positive temperature coefficients. For semiconducting materials, an increase in temperature will result in a decrease in the resistance level. Consequently, semiconductors have negative temperature coefficients. As with semiconductors, with an increase in temperature will result in a decrease in the resistance of an insulator. The result is a negative temperature coefficient. So resistance increases almost linearly with an increase in temperature to the inferred absolute temperature of minus 234.5 degrees Celsius. Another kind of material called superconductors are those conductors of electrical charge for which all practical purposes have zero resistance. The relatively low speed of electrons through the conventional conductors is due to the collisions with atoms and the repulsive forces from other electrons. So electrons in conductors offer absolutely no resistance to the passage of the electrical charge. Resistors are generally made in many forms, but they all belong in either of the two groups. Either they are fixed resistor or they are variable resistors. Fixed resistors are made out of metal films, high resistance wire, or carbon composition. Variable resistors have a terminal resistance that can be varied by turning a knob, dial, screw, or anything else appropriate for the application. Variable resistors can have 2 or 3 terminals. Most have 3. Variable resistors are classified as rheostats or potentiometers. Now, an ohm meter is a device that is used to measure the resistance of individual or combined elements. They detect open circuits and short circuit situations. They test semiconductors and electronic devices. You will be using ohm meter in your labs, and you have been using them, but be very, very careful. Never hook up a ohm meter to a live circuit.